Welcome to this explainer. Today we're diving straight into the ultimate dimmer switches of the digital world. We are looking at the foundational technology that literally powers all modern electronics. I mean, whether you're holding a smartphone, a tablet, or sitting at a high-end desktop right now, the absolute core magic happening inside that device comes down to one incredible breakthrough in material science.
But to really grasp where we are today, we gotta ask, what exactly replaced the vacuum tube? Think about those early computers. They were the size of entire rooms, and they ran on these clunky glass vacuum tubes that got crazy hot, sucked up massive amounts of power, and honestly, they just burned out all the time. They worked by shooting free electrons across a vacuum. We desperately needed a way to move away from those fragile, glowing bulbs to get to the sleek, ultra-fast electronics we use every single day. And the answer, it wasn't just building a better tube. It was an entirely new way of controlling electricity altogether.
Section 1. Meet the semiconductor, the sweet spot of conductivity.
Okay, so to understand the sweet spot, we have to look at specific materials, mostly silicon and germanium. Think of it like this. On one end of the spectrum, you have conductors, like copper, which just let electric current flow totally freely. On the opposite end, you've got insulators, like rubber, which completely block that current. Semiconductors, they sit perfectly right in the middle. And what makes them an absolute game changer is that they conduct electricity in the solid state. No glowing vacuum tubes required. This is literally the reason our devices can be microscopic.
But here's the really fascinating part. A semiconductor isn't just some static piece of rock. We can actually manipulate its behavior dynamically. We can change its conductivity just by hitting it with an electric or magnetic field. We can even change how it behaves by exposing it to light or heat, or, get this, by mechanically deforming a monocrystalline silicon grid. Because they react so predictably and precisely to these environmental factors, they make absolutely incredible sensors for pretty much any application you can think of.
Section 2. The magic of doping and how impurities create control. So the natural properties of semiconductors are great and all, but it's what human engineers do to them that actually kicks off the digital age. We use a process called doping. That's the deliberate addition of a tiny, tiny proportion of an atomic impurity, stuff like phosphorus or boron, right into the semiconductor base. It's kind of like adding a single drop of food coloring to a glass of water. It completely transforms the whole thing. By doing this, we massively increase the material's mobile charge carriers. Those can be free electrons, or they can be electron holes, which basically act like empty seats in a crowded theater that other electrons can just jump right into. By carefully picking these impurities, we essentially give the semiconductor its own custom electrical personality.
Which brings us to Section 3, P-type versus N-type, the epic battle of positive and negative.
Right, so when our doped semiconductor ends up with excess electron holes, it becomes a p-type semiconductor. The p stands for positive. On the flip side, when it has excess free electrons, it's an n-type semiconductor. And you guessed it, the n stands for negative. Now, it's worth pointing out that the vast majority of mobile charge carriers in these systems do actually have negative charges. But having these two distinct flavors, one positive leaning, one negative leaning, is exactly the toolkit we need to start directing traffic at the atomic level.
So what happens when we mash them together? We get the p-n junction. This boundary, right where the n-type and p-type connect, is the absolute core of modern electronics. The whole secret sauce of manufacturing complex integrated circuits is precisely controlling exactly where and how concentrated these dopants are on a single silicon wafer. When we control those junctions, we are literally controlling logic, memory, and computation itself.
Moving on to Section 4, the mighty MOSFET, the undisputed king of modern manufacturing.
This right here is the most successful application of everything we've talked about so far, the MOSFET. That's a bit of a mouthful, but it stands for Metal Oxide Semiconductor Field Effect Transistor. Whether they're used as single standalone devices or crammed by the millions onto one tiny microchip, it is the most common semiconductor device in the world. Just to put this into perspective for you, back in 2013, humanity was already manufacturing billions of these specific transistors every single day. Billions, every single day. It is the microscopic workhorse that literally carries the entire weight of the information age. And finally, Section 5, a trillion-ship world. The unimaginable scale of global production. Let's zoom way, way out from the atomic level for a second. 9.1%. That is the average rate at which semiconductor production has grown every single year since 1978.
Compounding growth at that kind of rate over decades means the physical infrastructure needed to build our digital tools has just been doubling and doubling and doubling again. It has completely transformed the entire global economy.
And all that compounding growth leads us to a massive, mind-bending milestone: 1 trillion. In 2018, shipments of semiconductor devices were predicted to cross 1 trillion units for the very first time. Think about that: 1 trillion devices manufactured, packaged, and shipped in a single 365-day window. The sheer physical scale of that is almost impossible for the human brain to truly wrap its head around. But somehow it gets even bigger. When you tally up all those years of continuous, accelerating production, you get well over 7 trillion. 7 trillion of these devices have been made to date. Honestly, it is very likely the most widely manufactured artifact in the history of human civilization. We have literally shaped silicon and electricity into 7 trillion tiny flawless logic gates just to compute, connect, and power our modern lives.
Which leaves us with one pretty profound question. With well over 7 trillion of these microscopic switches already powering our world, from the smartwatch on your wrist to the massive servers running the entire internet, what exactly are we going to build with the next